week we're focused on nuclear magnetic resonance, or NMR. This is a very widely used analytic tool to analyze samples. It's used in industry, and you'll be using it a lot in Orgo 2 lab. So we'll kind of get a preview of it this week in lab. So I'm going to talk about NMR, the theory behind NMR, like why it works. We'll do a couple of examples, and then we'll talk about what we're doing in lab this week. So NMR is actually used in MRI, or magnetic resonance imaging. Oh, that should say imaging, not imagine. But an MRI is widely used in the medical field, and that provides details about soft tissue. It's a similar process as what we're doing in lab as NMR. You use magnetic fields and radio waves to analyze the composition of soft tissue. So when you take an MRI, there's a large magnet and then radio waves that soft tissue is exposed to. And so the shading of an MRI image provides information about the makeup of the tissue. So I have an example of an X-ray and an MRI of a knee. So here you can see, let me get my laser pointer. In the X-ray, you can see knee bones. In the MRI, it provides a little bit more detail about the tissue around the bones, and a little bit more detail right here. Those dark pieces are actually tendons. So that's the ACL and the PCL there. So MRIs, super useful in the medical field, and MRIs are based on essentially NMR. So we're going to learn about very specific nuclear magnetic resonance for both protons, hydrogen atoms, and carbon atoms. And the reason this works is because all nuclei, which are made of protons and neutrons, they spin. And since in the nuclei we have charged particles, we have protons, that when those spin, that induces a magnetic field. So protons and neutrons, the nuclei, are always spinning. So as they spin, which is kind of shown here, you can imagine a nucleus spinning on an axis. It generates this magnetic field. Let me try to get a pen now, where we have kind of, just like we think about around the Earth, around a magnet, there's a magnetic field. We have a North Pole and a South Pole around the nucleus of an atom. So the spins of a nucleus can be affected by an externally applied magnetic field. So if you situate protons in a magnetic field, that'll impact their spin, because now you have something with magnetic north and south poles with a magnetic field being exposed to another larger field. So when a magnetic field is applied, protons will arrange to have spins either parallel or anti-parallel to the magnetic field. So if you imagine a sample of molecules, protons or nuclei are just arranged randomly, spinning in random directions. You then apply a magnetic field, and in this image, the direction north to south is pointing up. Then these nuclei will arrange to either be aligned with the magnetic field or anti to the magnetic field. The nuclei that are anti-parallel to the applied magnetic field exist at a higher energy state. And so that's exploited when we do NMR analysis. So thinking about, in this image, we have the energy of nuclei, energy of anti-parallel spins are pink, and then the energy of parallel spins are blue. As you increase the strength of the magnetic field, the difference in energy levels increases. So a stronger magnetic field, you'll have a greater difference between these two energy states. If the magnetic field is 0, the two energy states are equal to each other in energy. So with a strong magnet, we can increase the difference in energy between antiparallel spins, and parallel spins. So that means you have some nuclei that are existing at this lower energy state with parallel spins, and some that are existing or can exist at this higher energy antiparallel state. If your sample is then exposed to radio waves, the nuclei that are at the lower energy can absorb a specific energy, specific wavelength of energy, to then exist at the higher energy state. So in this way, it's very similar to the different, the other analysis techniques we've looked at, where molecules will absorb energy of a certain wavelength, and we detect the energy that is absorbed or the energy really that's not absorbed, and that tells us what the molecule does absorb. So when we're looking at NMR, the difference in energy between the parallel and antiparallel states is generally within the radio wave frequency. And so after we've applied the magnetic field and exposed the sample to radio waves, the NMR instrument can then detect which frequency of radio waves are absorbed by the sample, and that will tell you about the nuclei that are present in the sample. So the next image that I have on the next slide kind of shows this in a different way. So we've got randomly oriented nuclei. They're all generally of equal energy. We apply a magnetic field. We now have some nuclei that are aligned with a magnetic field in a plus state. We have some that are anti-parallel to the magnetic field in a minus state. So we have lower energy aligned with magnetic field, higher energy anti to the magnetic field. And then when you add radiation in the radio wave frequency, nuclei that are at the lower energy state, so the +1/2, can then absorb that energy to be at the -1/2. And so an NMR spectrum will tell you the energy that's absorbed by protons or by nuclei in the sample, and different nuclei that are in different bonding patterns in different chemical environments will absorb different energy waves. So I have an example of an NMR spectrum on the next slide for a molecule. First, I'll say that TMS is something that's often used as a reference point. It's a molecule that shows a peak at 0. So you can always make sure your instrument is working properly and aligned at 0. And so this is a proton, so an HNMR sample. HNMR, carbon NMR are both very common. Others are possible, and you'll learn about that in the videos that you watch. But in our class, and in, I believe in Orgo 2, you'll only focus on proton and carbon NMR. But this is an example NMR spectrum of a molecule that has protons, 2 hydrogen atoms, in 2 different chemical environments. So we have 2 different peaks. This is just that reference sample, so that's not involved, or that's not part of the molecule that's being analyzed. But we have protons in 2 different chemical environments, and so we get 2 different peaks. The location on the x-axis tells us information about the chemical environment that they're in. And the integration, which is not shown on here, we'll talk about that a little bit later. That also gives you some information. So there's 4 different features that are important when looking at spectra to really analyze the molecule or to determine what molecule is present. So the first is the number of signals. We saw in the last example that there were 2 signals for the molecule. So this is the number of peaks. And that tells you how many hydrogens, or the number of different hydrogens in distinct chemical environments. The next feature is the chemical shift of the signals. So that's the location on the spectrum. That is the chemical shift on the x-axis. So that gives you information about what we call electron shielding, the environment that's around those protons. If you have a hydrogen near an electronegative group, like oxygen, that will impact where it shows up on the NMR spectrum, and then that tells you that that hydrogen is near an electronegative group. Next is the integration of signals. So I mentioned this on the last slide. This is the relative number of hydrogens that correspond to each peak. So the relative number of hydrogens in each distinct environment. And then last is the splitting of signals, and that tells you the number of neighboring hydrogens. So if you have a hydrogen and you're taking proton NMR, the number of hydrogens on an adjacent atom can impact the actual peak that shows up on the spectrum, and that splits the peak. So we're going to go through each of these spectral features with a couple of examples to really analyze and determine what all of this means. So first, number of signals, or number of peaks. That again tells you the number of hydrogens that are in distinct chemical environments. We'll first look at methane. So this molecule, and we're going to focus on proton NMR or hydrogen NMR. So in this molecule, there are 4 hydrogens, and they are all bonded to the same carbon. If you look at one hydrogen, it's bonded to a carbon that's bonded to 3 other hydrogens. You could say the same thing for all hydrogens on this molecule. So all of these hydrogens are in the same chemical environment. They're equivalent hydrogens, and that means that methane on an NMR spectrum would show up just as one peak if we're doing proton NMR. Let's look at ethane. If we look at the hydrogens bonded to this carbon, they're all bonded to a carbon that's bonded to another carbon that has 3 more hydrogens. If we look at the hydrogens on the right, these are all bonded to a carbon, it's bonded to another carbon that's bonded to 3 more hydrogens. So all of these hydrogens on the molecule in ethane are also in the same chemical environment. So we now have 6 equivalent hydrogens. These will all produce 1 signal. So again, have 1 peak for ethane. So now if we look at propane, we have 3 hydrogens on this left side that are bonded to a carbon that's bonded to another carbon with 2 hydrogens. So these 2 hydrogens on the central carbon are in a different chemical environment than the hydrogens on this carbon because of the difference in bonding. So these 2 hydrogens will produce a different signal. So we'll get at least 2 peaks for propane. Now if we look at these 3 hydrogens on the right side, they are also bonded to another carbon that's bonded to 2 hydrogens that's bonded to the CH3 group. So these 3 hydrogens are in the same chemical environment as these 3 hydrogens on the left. So they'll produce the same signal as these hydrogens over here. So anytime you have that symmetry in the molecule, we saw it in ethane. You can imagine a plane of symmetry down the center of the molecule. We have the exact same hydrogens on either side. These will produce the same peak. In propane, you can imagine another line of symmetry right down the center of the molecule. These 3 hydrogens will produce the same peak as these 3 hydrogens. But overall in propane, we have 2 signals, so 2 groups of hydrogens. 1 signal corresponds to these 2 hydrogens, and then another signal corresponds to these 6. So the 2 hydrogens are highlighted in blue, and then the 6 are highlighted in orange. Okay, so these are 3 pretty simple molecules. We'll do a couple a little bit more complicated in recitation today, and then certainly in lab this week. So we've got number of signals. That's how we know the number of groups of hydrogens that are in distinct chemical environments. The second feature is the chemical shift, or the location on a spectrum. And that tells us information about the shielding environment or functional group around a distinct hydrogen. Just like IR, there are some ranges where we expect to see peaks for certain protons. So if you have this, like an aldehyde proton, for example, that's typically between 9.5 and 10 ppm for the chemical shift. If you have a saturated alkane or a hydrocarbon chain without any double or triple bonds, that's usually pretty low, between like 0.3 and let's say 1.8, 2.0. So there's a bunch of different groups on here. We have carboxylic acid, we have alcohols throughout the spectrum. But generally, the closer molecule or the closer protons are to electronegative elements, the higher energy they are, and that we say they're de-shielded or downfield. So a lot of new terms here. We say de-shielded because the electronegative atom takes electron density away from that hydrogen. So there's less shielding of electrons around the hydrogen. So that's why we say de-shielded. They're at a higher energy. They absorb a higher energy. And then towards the left, we call downfield of the spectrum, and towards the right is upfield. So higher energy, higher frequency, de-shielded, downfield. Okay. So generally, closer to electronegative elements, more de-shielded, more downfield, aka to the left of the spectrum. Okay, the next feature that we're focusing on is the integration of signals, and that's the relative number of hydrogens in each distinct environment. So we already looked at methane and propane. So methane, we said we have 4 equivalent hydrogens. We're only going to have 1 signal. So we could say the integration is 4, but usually that's reduced to the lowest integer. So it may show up as 1. So an integration of 1 for all these peaks. If we're looking at propane, we said we have 1 signal that corresponds to 200 hydrogens, 1 signal that corresponds to 6. So our integration ratio is 2 to 6, which we would reduce to 1 to 3. So if you were to take the integration of each peak, or the area underneath each peak, you'd get a ratio of 1 to 3 for propane. Now let's look at ethanol. So a new example, we haven't looked at this yet. We have a CH3 group, so all 3 of these hydrogens are in the same chemical environment. Then we have a CH2, so these 2 hydrogens are in the same chemical environment, and that environment is different from the CH3 group. And then we have an OH, and that hydrogen is in a unique environment. So for ethanol, we would expect to see 3 signals. 1 signal will correspond to these 3 hydrogens. 1 signal will correspond to these 2 hydrogens. And then 1 signal will correspond to this 1 hydrogen here. So then if we're looking at the integration of the peaks on the proton NMR spectrum for ethanol, we'd have a ratio of 3 to 2 to 1. That can't be reduced any further because we already have this one here. So the ratio of integrations will be 3 to 2 to 1. So if you don't know what molecule you have, but you do have the NMR spectrum and you do have the integration ratio, that tells you how many protons correspond to each peak that are present on the spectrum. Okay, then the last feature is the splitting of signals. And this is caused by the number of neighboring hydrogens. So this is really useful because it tells you not only how many peaks correspond to, well, NMR in general can tell you not only how many hydrogens correspond to each peak, but how many hydrogens are on adjacent atoms. So we say signals for a specific group of hydrogens are split by the neighboring hydrogens. And we use a factor of n+1 where n equals the number of neighboring hydrogens. Okay, let's go through this example to put some context to this. So this is ethanol, which we looked at on the previous slide. Let's focus on these 3 green hydrogens here. We have 3 hydrogens. This peak that these 3 hydrogens will correspond to are split by the hydrogens on the adjacent atoms. So this carbon only has 1 adjacent carbon. That carbon has 2 hydrogens. So in this case, n equals 2. So for these 3 green hydrogens, I'll come back to that table. They are split by these pink hydrogens, so that means that we will have n equals 2, add 1, and that gives us 3. So that means the peak that these 3 hydrogens will show up as on a proton NMR spectrum will look like a triplet peak. So a triplet, let me see if I can draw this here. A triplet peak looks like this. I'm kind of making it a little bit more dramatic here, where all 3 of these peaks correspond to these 3 hydrogens, but we have 3 different peaks within that signal for these hydrogens, and that's because this signal is split by these 2, and we do the n+1 rule to give us a triplet. So let me go back to this table now before we do the rest. So we said signals are split by neighboring hydrogens by a factor of n+1. So if you have a hydrogen without any neighboring hydrogens, then the peak will end up being a singlet, so just a single peak on the spectrum. If the hydrogens that you're focusing on have 1 hydrogen on an adjacent atom, the peak will show up as a doublet. So instead of 1 single peak, it'll be 2 peaks very close together. If you have two hydrogen atoms on the neighboring atom, so this is what we saw over here for these 3 hydrogens, that signal will show up as a triplet peak, where 1 peak is split into 3. If you have 3 hydrogens on neighboring atoms, that signal will split into a quartet peak, so 4 small peaks. If you have 4 hydrogens on neighboring atoms, that peak will split into a quintet or a multiplet, which we use multiplet because once we get in these higher numbers, it's hard to distinguish exactly how many peaks are there. So if you have 4 to 5 neighboring hydrogens, that'll show up as, sometimes we'll label it as a multiplet, sometimes we'll specifically call it out for what it is. Okay, so let's go back to this example. Now we're looking at these light pink hydrogens. We know that there are 3 hydrogens on this adjacent carbon. And then on this adjacent oxygen, there's 1 hydrogen. But often, if you have an electronegative element like oxygen nearby, this hydrogen doesn't impact the splitting of these atoms. So we'll say that these light pink hydrogens are split by these 3 green hydrogens. So that gives us a 3 plus 1, which equals a quartet peak. So these 2 hydrogens will show up as a quartet. And then lastly, we have this hydrogen here bonded to oxygen. Sometimes, because it's bonded directly to an electronegative element, we won't see any splitting. But we'll talk about the splitting in this case. So if we look at the adjacent carbon, that carbon is bonded to 2 hydrogens. So we'll say that this peak theoretically is split by 2 hydrogens and will also show up as a triplet. Okay, now let's actually look at the spectrum for ethanol, the NMR spectrum. So we said, looking at the CH3 group, so these green hydrogens, it should show up as a triplet peak, and that's what we see here. So this is that CH3 group. This is what the triplet looks like, where you have one larger peak typically in the center and then two smaller peaks on either side. For the CH2, so the light pink, we said that this is split by the 3 hydrogens over here, and we see that on the spectrum where we have a quartet peak for the CH2 group. In this case, I mentioned that often when you have a hydrogen bonded directly to an electronegative atom, that peak won't be split. This looks like it's really not split because you can't see the individual peaks on either side. Sometimes it's not resolved enough. We can talk about what we'd expect in theory and what is actually observed in an NMR spectrum, because there are limits to what an NMR spectrum can resolve. Anyways, we see this as the OH peak. And then I also want to emphasize, if we're looking at location on the NMR spectrum or the chemical shift, we see that the hydrogens that are closest to the electronegative atom are further downfield or further to the left. So we have the hydrogen directly bonded to oxygen all the way to the left. The hydrogens on the CH2 group, which are closer to oxygen, are further downfield than the CH3 group, which is furthest away from the oxygen. This is the NMR spectrum for ethanol. And then again, we have that TMS reference peak at 0. Sometimes that's present, sometimes it's not. So this next one that I show you doesn't have the TMS peak. We're going to look at the NMR spectrum for propanaldehyde. So propane, we have 3 carbons total. And then aldehyde is a carbonyl with a hydrogen. So a carbon double bonded to oxygen and a hydrogen. Here we have the NMR spectrum, and then we'll match the peaks to the different hydrogen atoms in the molecule. Okay, so first we have a CH3 right here. We have 3 hydrogens that have 2 neighboring hydrogens. So this would, we would expect to see a triplet peak. On the next carbon, we have a CH2 that is split only by the hydrogens on this neighboring carbon. So the green hydrogens, we'd expect a, actually I'm wrong, it would also be split by this hydrogen here. So I have quartet on here, but this should be a quintet or a multiplet. And then lastly, we have this hydrogen. This carbon isn't bonded to any other hydrogen, so this we'd expect to see a singlet. This hydrogen is also closest to our more electronegative atom, so the most downfield peak corresponds to the singlet hydrogen here. The CH2 group is closer than the CH3 group to this electronegative atom, so the CH2 group shows up right here at about 2.5 ppm, and then the CH3 group is the lowest at 1. Okay, so we'll do some more proton NMR examples in class. We'll talk a little bit about carbon NMR, which operates very similarly to proton NMR, but it tells you information about carbon atoms. So it's a little bit less sensitive of a tool, but it's still useful. And then one of the differences is that carbon NMR signals are split by the adjacent carbon atoms. So the carbon atoms directly bonded to whichever atom you're focusing on. Another difference is that the ppm values are much higher for carbon NMR spectra. So this is a general range where we have Saturated carbons without any double bonds at lower ppms or more upfield. And then unsaturated, so we have double and triple bonds over here, are further upfield. So this spectra that shows you chemical shift values is included in the document you have on Blackboard. So I just want to do one example for carbon NMR. We're looking at ethyl propyl ether. So this is an ether because we have an oxygen bonded to two carbon chains. One is an ethyl group, so CH2, CH3, and the other is a propyl group, CH2, CH2, CH3. And here I have the carbon NMR spectrum. And you can see it's really difficult to tell the splitting of these peaks. So for this example, we will just be determining if this molecule matches the spectra based on number of peaks and peak location. So I have highlighted the different carbon atoms. Now each carbon atom in this molecule is in a different chemical environment. So the CH2 is different from this CH2 because this one is bonded to another CH2 while this one is bonded to a CH3. And then this CH3 is different from this CH3 because of its proximity to the oxygen atom. So each carbon atom is in a different chemical environment. We would expect to see 5 different peaks, which we see on this NMR spectrum. And then just like in proton NMR, the carbon atoms that are closer to electronegative atoms are more downfield. Okay, I wrote that wrong. They should say downfield. So our yellow and green peaks are these 2 peaks over here that are more downfield.